Okay, let's get started. Okay, so last time I said that so for x over a field of characteristic P, smooth and projective, there exists some union of components locus G check restricted prime such that this category of sheaves with nilpotent singular support on bun G was equivalent by some Langlands functor to this indco nilp of locus G check restricted prime. And I said that this implies that the space of compactly supported automorphic forms is then isomorphic to global sections of locus G check arithmetic prime with coefficients in its dualizing sheaf, where this locus G check arithmetic prime is the base change okay, so so I guess I'm going to give it's sort of convention. Well, I'm going to try to mostly ignore the primes because it's not going to matter for anything in the discussion today. Also, we're going to be mostly on the spectral side today anyway, so it doesn't really matter. At some point, I'm going to, well, we're going to keep automorphic forms in the back of our minds, and you can just add the primes as needed.
What was the expectation about prime? Is it expected to be?
It should be everything. Yeah, exactly. It should be that you can ignore the prime. You definitely can ignore the prime for GLN. Yeah. So this, the difference is just sort of like, in some sense, it's the question of, given a Langlands parameter, does there exist a corresponding automorphic form? Okay, so there's a couple motivations for what I want to say next, but the overall goal is to make the right-hand side more explicit. This global sections with coefficients in the dualizing sheaf. And so there's a couple motivations. So one was that yesterday Mitya asked the following. So we have this quasi-co of locus G check restricted. So that means the geometric thing. This maps to indco. This is a functor that preserves compact objects, and you can put nilp if you like. And this gives rise via trace of Frobenius to a map from functions on locus arithmetic to sections of the dualizing sheaf. And the question was sort of like, what does this map look like in practice? So that was one just sort of question that was, I don't know, staring us in the face. And the other motivation is that in pretty large generality, Arthur formulated multiplicity conjectures that should describe the space of automorphic forms. And it's not clear where these are on the right-hand side. And so what I want to do is analyze kind of the right-hand side, so to say, to death in order to kind of understand what's really happening for what this isomorphism is really saying. Questions?
So there's also a map in the other side? I mean, there's also a map from NCO to QCO, and does this induce a map?
No, because you need the map to preserve compact objects in order to get a map on traces. So the trace formalism what it said is that if you have this functor from C to D, and it has a right adjoint, so it's supposed to have a continuous right adjoint, which is in practice the same as this functor preserving compact objects. And you have this endofunctor T and this endofunctor S, and you're given a natural transformation. What was it? Probably Ft to SF. Yes. Then this gives rise to a map of traces, some sort of canonical map like this. That's the general formalism. And so the point is, when you map quasi-co to int-co, it satisfies that hypothesis of having this right adjoint, which is very essential for getting the map, even though it's not in the setup for this intertwining property. Well, it's not in this part of the setup. The right adjoint is absolutely necessary to get the map of traces. And yeah, so that works for this functor, but not for the other functor. Other questions? But yeah, we'll see that as an important subtle point. OK, so what I'm going to do is define. So yeah, so we're just sort of purely on the spectral side. I'll keep with the G checks mostly to keep things motivated, but yeah. So maybe the first theorem is the following. So yeah, and I should say maybe everything today is joint with Dennis and Vincent. OK, so first let me sort of formally answer Matthew's question. He's not here. OK. And then we'll get into a little bit finer structures. But this theorem already gets you pretty far, so you can reference it with a number. So the first thing is that, OK, this isomorphism kind of miraculously tells you that the right-hand side is concentrated purely in cohomological degree 0, which isn't an obvious feature. And it's an extremely roundabout proof of that fact. But let me say the following. You can also work directly with functions. And the statement is that this is in cohomological degree 0, is a actually reduced commutative algebra. So it's in degree 0. There's no cohomology. It's a usual algebra, and I'm saying it has no nilpotent elements. The next thing is that this basic map from O to omega is actually injective.
Sorry, but do you know that without the prime, independently of everything, that when you do global sections of omega, that it's concentrated in degree 0?
Okay, we're going to do finer statements, and those imply that.
Okay, right.
Yeah.
But but just purely formally, the statement.
Purely formally, I'm cheating. Absolutely, yeah. But it's I follow it. It's yeah. But also I'm in my convention of ignoring the primes, and so yeah. Purely formally, you're correct. Yep. And then the third statement is that under this Langlands equivalence, this element 1 inside of global sections of loxus with coefficients in O corresponds to the Poincare function, which is equal to the function of the Poincare sheaf. And let me remind that this global sections of loxus with coefficients in O was called the excursion algebra. And so what this says is that we get the following sort of picture. So there's this space of compactly supported functions on bungee of Q, these automorphic forms. It's the same as global sections of loxus, G-check, arithmetic. There's a prime if you want, but I'm going to stick hard to my conventions. And then here there's the subspace. And over here, what are you getting? So you're getting the excursion submodule generated by the Poincare function. And it turns out that this is actually a free module of rank 1 is kind of what this picture is saying. Questions?
Is it possible to give some kind of description of the non-compactly supported functions on the Langlands dual side?
No.
That seems like, really?
Can you just do something about Eisenstein series?
Yes, well, we did say something about, we said something about pseudo-Eisenstein series, which is as good as saying something about Eisenstein series. Let me come back to both of these questions soon. Okay, so a little bit more generally, so I'm going to define a filtration on this category indco nilp. So in other words, just a nested sequence of subcategories indexed by dual nilpotent elements, nilpotent orbits. so namely, the filtration term for E on this indco nilp is going to be, by definition, I think, no surprise, is that this, sorry, there's restricted everywhere.
It's the only thing that makes sense, so why do we have to write it?
I know, I agree.
I mean, if prime is easier to write than REST.
Yeah. No. I mean, it's. Of course, you're correct. It's because there's somehow people can genuinely get confused about the difference between this locus restricted and this locus arithmetic. So I sort of want to be systematic about the difference. Of course, I only talk about, when I talk about indco, I'm talking about the geometric theory. When I'm talking about functions and things like that, I'm talking about the arithmetic theory. Except for a couple days ago when we talked about functions on the Deram stack, on the Deram version of Luxus. But that's not what we're doing today. It's just the difference between the two things is very essential. And so, whereas the difference between the prime and the not prime is not essential today. Okay, so so I have this filtration by a series of subcategories. So what is this? So this so the way the Arinkin-Gates-Gorey theory works is that you get a category indco of lambda of a stack y inside of indco y whenever y is quasi-smooth and lambda is contained inside of what's called the -1 shifted cotangent space to y. And so when y is equal to any version of local systems but on a curve, then this -1 shifted cotangent space is the data of a local system plus a section phi inside of the cohomology of the adjoint local system with a shift by 2. And if you're being really careful, then there's sort of, in some sense, a Tate twist by 1 also. There's some duality, which you can ignore because it's talking about the geometric theory. And so what I'm saying is, in this case, this indco nilp is this. It's this thing for lambda being. Oh, I should have said lambda in here is closed and conical. And it's this thing in the case when lambda is the locus of sigmas and phis such that phi is nilpotent. So that's an equivalent description. And then I can say more generally that phi, so I guess for me, nilp E is, or let me put a less than or equal to E just for my own sanity for a second. This nilp less than or equal to E. So by definition, a local system, sigma, like a G-check local system, is a functor from representations of G-check into local systems on X, like Lee's sheaves on X. And so I just take the adjoint representation, and I get some honest local system. So I can't talk about the cohomology of a G-check local system. To do that, I need a representation and addition, and yeah. But if we're talking about GLN, what this means is this is a rank n local system on X. And this is the just endomorphisms of that local system. That's what G-check sigma is in that case. So, Okay, so this is some version of like the moduli space of Higgs bundles, but in a which is the cotangent space to Bun-G, but it's in some local systems analog instead. Okay, so nilp less than or equal to E is the data. It's the pairs sigma and phi, such that phi restricted to any point x is in the orbit closure of E. So the 0th term of my filtration, this is just when, so that corresponds to the 0 nilpotent element. That's asking for incoherent sheaves whose singular support is 0. And part of the Arinkin-Gates-Gorey theory is that that's just this quasi-co of Luksus G-check restricted. Fill of the sort of principal nilpotent is exactly int-co nilp. In general, I have some kind of nested sequence of subcategories. I'm not going to try and draw the diagram. Indexed by these nilpotent orbits and their natural post-set structure.
One thing you can try to do is to take several nilpotent orbits such that neither of them is contained in the closure of the others, and define and take the category of local systems such that the restriction is contained in the closure of all of the nilpotent orbits. Can you reduce it to the nil lesser than E somehow?
I don't totally understand the...
I'm saying that not every G-equivalent closed subset of the nilpotent cone will be of the form orbits in the...
Okay, this is true. This is true. So really, I should say this a little bit better. You're correct that what my stratification is really indexed by is sort of like downwardly closed subsets of the nilpotent cone mod G-check. That's a better formulation of what this is getting at. But what I'm really going to care about is, let's say, similarly for nilp less than E, so I ask that it be in the orbit closure minus the orbit. And so now by trace of Frobenius, this gives a filtration on global sections of Luksus G-check omega, and so on these compactly supported functions of Bun-G of FQ as well. So let me just give a couple orienting comments about that. So first of all, an example is when G is, I guess, SL2, then this fill zero of compactly supported functions is going to map to compactly supported functions on G of FQ. And now this maps to my field E, it's QL bar, which turns out to be the associated graded piece for the principal nilpotent element. What is this map? This map is just integrate the compactly supported function, and so these are the set of functions whose integral is 0. Well, integral just write as integration. And integration, the Bun-G of FQ is really a groupoid, so every point carries some automorphism group. And so you should weight the point by 1 over the order of the automorphism group. So you weight against the natural measure on this space when you do the integration.
And the Poincare function, can you explain how it sits with respect to this filtration?
Yeah, it's in the 0th term. That was basically, so yeah.
So is the 0th term equal to the orbit of the excursion algebra under the...
That's right. So what this is saying is that this is isomorphic to the excursion algebra for G-check in this case. That's sort of this general thing for Vil 0, where the element 1 inside of here corresponds to this Poincare function. Yeah. Which conveniently does have the property that its sum is 0. Yeah. Does that answer the question? Yeah. Yeah. Okay. So that's the picture. And yeah, and so
So are the associated related pieces also like free models or?
Obviously not.
No, not free, sorry. Like secret. Well, I don't know.
amazing question. Yeah. Okay. First of all, yeah. So the filtration, basically, like this filtration at the categorical level, was preserved under the action of quasi-coev loxus G-check everywhere. If you tensor by a perfect complex, you stay in this subcategory. And so therefore, this filtration is a filtration by modules over the excursion algebra. And you can ask, what do you get? And so let me tell you. Let me take IE to go from SL2 to G-check, the Jacobson-Morozov SL2. It's not wrong to write an S, is it? Is it Z? Associated with E. And I'm going to always let HE be, by definition, the centralizer of this homomorphism inside of G-check. And so HE is, we call it a linearly reductive group. So in other words, it's a possibly disconnected maybe disconnected, but its connected component is reductive in the sense we've been discussing. And I guess I'm always going to consider loxus HE arithmetic mapping to loxus of G-check arithmetic via a certain slightly funny map due to Arthur. So there's an obvious map in this direction because HE maps to G-check. And that's not the map I'm going to use. So what I do is I take sigma, an HE local system. So let me kind of say this a little bit lazily. So this is the same thing as a representation from Wx, from the Weil group for x to HE of QL bar. And I can think about that as the same thing as a representation from the Vey group times SL2 into G check, QL bar if you like, which gives rise to, so this is sort of my sigma, and this is my sigma times times this IE. And then what I'm going to do is then, so I restrict this map along the map from the Vey group times SL2, no, the Vey group into the Vey group. Sorry, I've given myself made a mistake yesterday and did that. Times SL2, which sends an element G to itself, and then the matrix, which is the absolute value of G to the 1/2, and then this is the absolute value of G to the minus 1/2, where absolute value means I take the Vey group, it maps to Z, and then I map this to, let's say, E star by sending 1 to Q. And this is my absolute value map. And I can also make sense of absolute value to the 1/2 because secretly I chose a square root of Q.
Do you have a conceptual explanation for this funny map?
Yeah. Ultimately, it comes from this Tate twist. But I haven't said anything about the funny map. It's just that when I think about Loxis arithmetic, that's always going to be the map that I want to think about. And so what we're going to do is we will construct.
But that Tate twist, you didn't really, I mean, the way you define Loxis G-check arithmetic, the Tate twist shouldn't actually appear, right?
I haven't said anything, right? So it doesn't.
Like, yeah, you have to kind of twist more. Or what to say? I mean, there's this notion that the Langlands parameter needs a cyclotomic twist as well, that you have to kind of put into the definition in principle.
This is the cyclotomic twist.
Yeah, you're putting it in there, well.
But that's.
But when you say cyclotomic twist, are you thinking of the local picture? I think there's something kind of confusing there about, there's like, in that situation, there's kind of two SL2s in some sense, and here there's just one SL2.
Yeah, but still, I mean, if you literally calculate the cotangent space to your stack, then you don't see any Tate twist just because you didn't put any, I mean, at no point did you put any Tate twist in anything. Or, oh, it's because of Tate duality, or sorry, local, it's because of duality on the...
Yeah, it's because of duality on the curve, yeah. So what I'm saying is, if the precise statement is like Frobenius acts on this y, and if you want to describe the cotangent space Frobenius equivariantly, then you need the Tate twist.
Right, okay, I understand that, thanks, yeah, I retract my comment. Thanks for explaining.
But we haven't used that cotangent space in any serious way, so it hasn't occurred in any construction we've done so far.
But how does this manifest itself as an element of an SL2?
Well, I mean, I hope we'll. No, I'm exactly hoping that we'll get there. Yeah. Okay, so what we'll do is we'll construct something I'll call LE, which is a line bundle on this Loxis HE arithmetic. Actually, it has the property that its tensor square is equal to O. LE is actually equal to O if E is even. And then the theorem is the following. So there exists an isomorphism between the square E of global sections of log-sys G-check arithmetic with coefficients in omega. So this is isomorphic to global sections of log-sys of HE with coefficients in LE. And this is isomorphism of modules over the excursion algebra. And I say there exists an isomorphism. There exists a canonical isomorphism, and I'll hopefully tell you how to construct it before the day is over. And then the second thing is that this. So you can ask, what is this like? Like, make this more explicit. And then the second thing is that there exists a decomposition of log-sys HE arithmetic into two pieces. So it's a two connected components. And the statement is that this is equal to 0, and this is equal to a well, finite. It's isomorphic to global sections of log-sys HE plus arithmetic with coefficients in O, maybe a little non-canonically.
So is everything we're ever going to discuss here concentrated in degree 0?
Oh, yeah, that's a great third point. So
like, so this filtration is actually by sub-objects, et cetera, et cetera.
Right, and so the maybe really important third point is that this global sections of log-sys HE coefficients in L is, well, okay, corollary. This is concentrated in degree 0. So basically, I told you before, I mean, there's this stuff about like linearly reductive, but really the theorem I stated before about being concentrated in degree 0 works for linearly reductive groups. And so,
yeah. So then from this and some kind of induction, you also deduced that all of these less than or equal to E guys also live in degree 0.
Right, exactly. So the corollary is that this filtration on the filtration on global sections of G-check arithmetic coefficients in omega we constructed was a filtration in the usual sense. So this filtration we constructed on this in the derived category was a filtration in the usual sense, which means all terms are in degree 0, and all maps are injective.
This is a filtration indexed by a poset.
This is a filtration indexed by a poset.
Uh-huh.
Yep. So other than that part, yeah. But if you talked about a filtration indexed by a poset in like 1950, it would be the same notion. filtrations indexed by posetsets must be in Bourbaki, right? Yeah. Let me make a remark, which is that very, very a posteriori, it seems there exists a roundabout proof that I mean, OK, I'll just put one very just to be less. There exists an argument that I learned from Daniel Lee Huerta, but I guess it's an obvious thing to well-educated people. OK, that there exists an argument that in this everywhere unramified situation, this log-sys HE arithmetic plus is actually equal to log-sys HE arithmetic, meaning that you kind of could ignore that whole business about pluses and minuses. But I'm I sort of want to forget this fact because philosophically the story doesn't need it, and I think that it's a little bit more. If you're trying to extract like knowledge from this situation about how Langlands is supposed to work or something, I think that it's better to forget that fact.
You're right. It's probably still a good question. If LE will actually be the starting sheet in some cases, how is it that the restriction of global systems to this S minus is 0 when LE is O?
Wait, say the question again?
If LE is automorphic to O at least sometimes, how can the restriction of the global sections to S minus be 0 in these cases?
Oh, it can't be in those cases. Yeah. So this is something. Yeah, it just. I can tell you very briefly the recipe. So let me say a little bit more about this decomposition, which will make your question more obvious. So you ask yourself, are you in the even component or the odd component, right? What should you do in order to check this question? So first, I'm going to tell you, pass to your semi-simplification. So you take a local system, and just maybe it wasn't semi-simple, semi-simplify it before running the algorithm. So now you have a semi-simple, that's in the same connected component, so it was fine. So now take your semi-simple local system and run the following game. So take this LE and restrict it to the classifying stack associated to that point. So that's a copy of the classifying stack of the automorphism group of your local system, your semi-simple local system. And so in that way, like this is actually really like a mu2 torsor. So what you're going to get is a map from the automorphism group of sigma to z mod 2. Now what you need to do is check, is that homomorphism trivial or non-trivial? If it's trivial, then you're in the even component, and if it's non-trivial, you're in the odd component. And so in particular, when LE is equal to O, that local system was, that mu2 torsor was trivial, and so there was nothing to do. So everything was even in that case. Yeah.
For the field, for the underlying field for the local system, it must have a non-positive characteristic, right? It must have a 0 characteristic.
Yes.
Because otherwise, in Frobenius, we have a twist, right?
So there's an assumption everywhere that my field has characteristic. I'm working with QL bar sheaves everywhere. Yeah, in the story. And QL bar value functions.
And so we restrict it basically to Betty and the RAM, right?
No, this is an étale story, so that I can work in positive characteristic. So my field K has positive characteristic. What I was saying in the beginning of the talk, which was continuing from last time, is that we have fully faithfulness of the automorphic to Galois direction in characteristic P for A tall sheaves. And so,
And if we have a positive characteristic, won't the Frobenius automorphism have a twist?
but positive, maybe we can discuss afterwards. So there's two fields here. One is the field my curve lives over, and my group G lives over, and that's for me an algebraic closure of FQ in this case. And I need that in order just to talk about Frobenius at all. And then the second field is kind of my coefficient field. So like all of my sheaves, all of my local systems, they all live over that second field, and that's QL bar. And so that's the situation. And there are various twists involving Frobenius, like the one I maybe just erased, but yeah. Yeah. Okay, so are there questions at the moment? Okay, so now I guess I want to discuss the application to automorphic forms. So the first thing is, I guess, let me, so I have this filtration, and let me consider the associated graded of this space of compactly supported functions. And this I'm going to call fake automorphic forms. I haven't constructed LE, so it's. I just claimed that it exists. Yeah, well, we boxed it for now, and also there exists an isomorphism is such a weak statement. So yeah, I should before the end of the talk fill in those kinds of details. I agree.
At least there exists an argument that log sys HE plus is equal to log sys HE. This is a statement.
Yeah, this is a statement. Yeah.
Yeah. So it means this minus one is undebatable.
It means the minus part is empty. Yeah. The basic idea is like, so here we have some character that here we have some character kind of the stabilizer groups, like I was saying before, and that character is what controls the plus and minus part of the story. I haven't told you the construction of the character yet, but I will. And also, Arthur constructed a similar character, and I would say, using epsilon factors. So like, and so the way the argument goes is like, first you compare our character to Arthur's character, which is not it's like a routine calculation, but they're not obviously the same, and they have different flavors. And then second, use this formula for epsilon factors as products of local terms, tells you that actually, if you have a symplectic local system on a global curve, it's sort of clear to see that you get some kind of epsilon factor, which will be either 1 or -1. But in fact, it's always 1 by this factorization formula. That's the phenomenon that's happening here. So it's ultimately like comparing what we do to what Arthur does with epsilon factors, and then second, using this funny factorization formula for the epsilon factors.
Yeah, I'm confused with the logic. So this corollary, like this thing is concentrated in degree 0. How did you deduce it?
How did I get that? Well, so okay, so what I
The first corollary.
Yeah, by the isomorphism there.
by the isomorphism. So what I'm saying is the associated graded term is first of all global. Is it somewhere?
Okay, from the first corollary to second corollary is fine. Like the first corollary.
So what I said earlier in the talk, part of theorem 1, was that these local systems, global sections with coefficients in O, is concentrated in degree 0. Yeah. That works for general linearly reductive groups. Yep. Yep. So yeah, exactly. And this also is supposed to answer Dustin's question from a long time ago. How do I know global sections with coefficients?
And omega is in degree 0.
Oh, I see. Because it's filtered in terms of things measuring global sections of O.
Yeah.
Yeah, and I should say maybe that all of the stuff about being concentrated in degree 0 and the structure of these global sections, it's all heavily uses Delin's theory of weights and Laurent-Laforgue's theorem that sort of every local system is iota mixed, which I guess hopefully we'll get to discuss more soon. But I want to say that there's that's a heavy theorem. Okay, so I called these fake automorphic forms. So let me just kind of comment about this naively for a second. So so remark 1 is I want to say that the constant function 1 is an element of this sort of thing here. So it's kind of, so this is the constant function. That's not really a meaningful statement. But what I can say is, for example, look, the associated graded was like the top associated graded term for a simply connected group anyway. It's always going to be just this one-dimensional vector space. The map is always going to be given by summing. And so I can sort of pretend that this is some incarnation of the constant function itself. And on the GUR, it makes sense. Yep, exactly. And remark 2 is, if you imagine working in L2, L2 completions, where you should sort of really descend everything to Q, maybe using the standard conjectures or something, and then complete. Of course, the filtration splits. And so I would say that sort of for Dustin's question about can you work with some, or is it possible to do some version of this theory with non-compactly supported functions? I would say that's a confusing question. Definitely lots of us were confused about it for a while. And now I would say that the right thing to consider isn't the space of non-compactly supported functions. The right thing to consider is the associated graded, and then to sort of pretend that these fake automorphic forms are honest functions, which is something that should be in some sense. No, it doesn't. Yeah, that. Yeah.
But then it's just a vector space, or like canonically speaking.
Well, what I'm saying is that what I expect is that you can descend this filtration over Q. Actually, I guess now that's a theorem. Oh, sorry, I have to be careful in saying that. No, sorry, it's a theorem that the excursion algebra descends over Q. It's very reasonable to expect that this filtration itself descends over Q. So we're talking about vector spaces defined over QL bar. Maybe Q adjoin the square root of Q is necessary. Yeah, I want. Let me just say Q adjoin the square root of Q. So I sort of will want to. I'd rather have it descend to like a totally real field, basically. Because then I mean we're talking about like, well, at that point we're talking about functions that maybe Q bar versus totally real field is not necessary. No, yeah, I want to keep it. Okay, so then we're talking about like, that's telling you that then you can pass to the real numbers or to C. There's some obvious inner product on this space, just sort of summing F times G bar. You can take L2 completions, and I'm saying that, well, I expect that to be a well-behaved operation in this situation. And that would then split the filtration. Well-behaved operation, for example, in the sense that if you pass to the closure of, so you take the L2 completion of like these compactly supported functions, then pass to the closure of each of the terms in the filtration, and then intersect back down with the compactly supported functions, I think you should get back the original filtration you started with.
But there's still a well-defined question of whether these extensions split as modules over the excursion algebra.
Yeah,
but it doesn't. It doesn't. Yeah. Yeah, you can't, like just this, in this case of SL2, you can't split this filtration.
But what would your L2 story be doing? Like,
then you split it by taking the function 1, which is in the L2 completion of compactly supported functions.
And that would still be, okay. Then that you expect that to be linear over the excursion algebra.
Yeah.
Okay.
I mean, I'm just saying it's like you're passing to some orthogonal piece, so it's completely functorial.
So it is a splitting as modules over.
It's a splitting of modules over the excursion algebra, yeah, but only once you do the completion.
Yeah, that was my original question.
Oh, okay, yep. That's sorry. Maybe I misunderstood. Yeah, that's the picture.
Mm-hmm. Yeah, because I was confused what the important statement versus this. Like, if it's just vector spaces, then this is obviously split.
Oh yeah. Okay, I understand your point. Yeah, but it doesn't split as modules over. Yeah. Yeah, so like, maybe let me comment about this for a second. So I mean, you can talk about like what are the eigenvalues of the excursion operators on this one-dimensional vector space. They're going to be the same as for the constant function 1, no surprise. So that's like this feeling that it is the constant function. I mean, of course, it's like inner product against the constant function in this case. And then in addition, what do I want to say? So if you split this obviously in an excursion equivariant way, the resulting like function in here would be a Hecke eigenfunction. And there's a lemma due to von Sohn-Laforgue that actually every Hecke eigenfunction that's compactly supported is cuspidal. That just sort of for free being an eigenfunction forces cuspidality. And so, yeah, I would have to correspond to a cuspidal eigenfunction.
For example, all the eigenfunctions in fake automorphic, all the eigenfunctions in the L2 story will show up as eigenfunctions in the fake automorphic forms.
Yeah, exactly.
Okay.
Yeah.
Okay.
Yeah. So, so similarly, define why I? Let's just define the fake discrete automorphic functions as those with as those fake automorphic forms that are locally finite under the excursion algebra action. So that means that if you take your function and take the span, this should be finite dimensional. Yeah. And let me maybe make one remark here. So if this F is in Ger E, then you can see that, so there's sort of an action of this excursion algebra for H also on F, and you can see that this is finite dimensional as well. The map from these H local systems to G local systems is finite. Okay, so now there's a what do I want to say? Well, okay, first of all, I guess I should say at some point the remark that this is all supposed to just be kind of, you know, encoding exactly Arthur's ideas about what automorphic forms look like. So what you should say at this point is that kind of maybe like at first approximation, what you might think the Langlands conjecture says is something like there's a bijection between automorphic forms of some flavor and some kind of Galois parameters of some flavor. And we would sort of enhance that to the statement that compactly supported automorphic forms is just the same as functions on locus. And what Arthur's supposed to tell you is that first there's a correction involving this Arthur SL2. So this is telling you that, well, and second, there's a correction involving these epsilon factors, these sorts of signs. And that's exactly what this is supposed to be telling you. Up to this version, up to this thing that you get confused about the filtration versus its associated graded. So it's really sort of describing fake automorphic forms, which are as good as automorphic forms for these purposes.
So how do you see the automorphism formula in this business?
Well, it's, I mean, sort of most, like everything here is like locally unramified. So if you see what the formula is saying in that case, he says that there's this character of the automorphism group into mu2, the automorphism group of your Langlands parameter, or of your Arthur parameter. And and the multiplicity formula is telling you that the multiplicity is either 1 or 0, depending on the sign. So that's sort of exactly what was written here. And that's just literally unwinding what the formula says when all of the local terms are kind of trivial. Other questions? Okay, and I guess let me write what I said on the board above. So Vincent Laforgue has this nice lemma in his work on the stuff that if you take cuspidal forms on Bun-G of FQ, so this is functions defined just like in the global situation. So there are these constant term maps, and these are the compactly supported functions whose constant terms are all 0 or not compactly supported. These cuspidal functions are exactly the locally finite vectors. And maybe here I should assume G is semi-simple at various points for convenience. Just otherwise, you have to say some extra words about the center. Okay, and sort of one of the big applications of this stuff is that, so suppose you have a point in this GER-E of locusis HE arithmetic, which is this sort of fake, well, let's say that this is an eigenfunction. What am I saying? Yeah. Well, let me even think of it as a compactly supported function. An eigenfunction for this, or even better, for the excursion algebra for this HE. So in this case, we obtain a semi-simple homomorphism from this Vey group into this HE of QL bar as the corresponding eigenfunction. Or what's the same, we get this map from SL2 times the Vey group into a G-check of QL bar, so to say. This is really SL2 of QL bar. And with the property that that this is the sort of Langlands parameter defined by Vincent Laforgue. But let me call this up top the Arthur parameter, or we can also call this the Arthur parameter. And the nice thing is that this this Arthur parameter is automatically actually irreducible. Meaning it does not factor through a parabolic subgroup. There's like let's say I take that in this meaning. Otherwise, you have to there's a slightly more restricted class of parabolics, which is appropriate for disconnected groups, namely the contracting loci of characters into the maximal torus. And so, yeah, so I'm making a claim now, which is that sort of from the picture I said so far, you can get that this Arthur parameter is irreducible. And here's basically the proof. So just like take A to be this excursion algebra for HE, but take it, it's really sort of any reduced ring over commutative ring over some algebraically closed field. And then suppose you're given M inside of A some one-dimensional submodule. Then really, so M, of course, is isomorphic to E, and A is isomorphic to A naught times E as algebras. So you have to be careful to like really use the reduced rings. You have to use the hypothesis that that the ring is reduced, because you can have sort of associated maximal ideals that cause you trouble in general. So just put a slight like counter example, so to say, to be aware of in this is you take E of xy mod xy and y squared, and inside of here there's the submodule generated by, I guess, y, and so that's really a submodule, because if you multiply by x you get 0, and if you multiply by y you get 0. And so, but this doesn't split as algebras, and of course it's not reduced. And so what that's telling us now is that we have sort of the following picture. So like, so roughly here's all our loxis HE arithmetic. But now here's my isolated point. This is my sigma Arthur. And so what we got was that this point, well, and how should I say, this is really, I should say it slightly better. It's the spectrum of the excursion algebra is what I'm drawing here. And so our point has to be just really a zero-dimensional point, an isolated point inside of this moduli space. And now the claim is that if you have a semi-simple map, let's say from the Vey group into this HE of QL bar, that is not irreducible, then the corresponding point is not.
Well, I'm confused. The sigma Arthur, it lies in the spectrum of excursion algebra for HE or GJ?
For HE, because I said it was really even better. It was an eigenfunction for this excursion algebra for HE.
But why is it isolated? It would be. Did we assume it's also reducible for HE? Or?
So what I'm trying to do is prove that it's irreducible.
Okay, I see.
So so there's.
Sorry, you use this lemma to.
Yeah, so there's something kind of non-canonical that's happening here. So what's happening is like I'm starting with something which is an eigenfunction for the excursion algebra for G check, and then I'm saying by hook or by crook, I don't really care. A little bit non-canonical, maybe upgrade it to find some Arthur parameter that enhances that. Here's the procedure for doing it, just namely, you are an eigenfunction for the excursion algebra for G check, but then there's sort of this thing finite over the excursion algebra for G check acting, and so you can make it an eigenfunction for that as well. And then you get a Arthur parameter. But now my point is, once you are an eigenfunction for that excursion algebra, then actually, well, there it splits as a product. So it's really an isolated point here. And so, yeah, so then what I'm claiming is, OK, so it corresponds to some point in the spectrum. Now we have to be a little bit careful about our GIT. So points in the spectrum are semi-simple local systems. That's what the E points are, the QL bar points. And so I'm claiming that this isolatedness is actually just enough to force it to be irreducible. And the idea is the following. So I'll do the amazing trick of proving the contrapositive or whatever. So if you start with some semi-simple parameter, and suppose it's not irreducible. So if it's not irreducible, that implies that there's some co-character from GM into this HE. So sigma factors through its centralizer. And so now what I want to do is I want to try and flow my point to get some other points in order to see that it was not irreducible. And the way I do that is I modify sigma by only changing what Frobenius does. And then exactly using this lambda check. So for every element of GM, so I guess this gives rise to a map from GM to this Luxus, well, to the spectrum of the excursion algebra, let's say. Luxus HE arithmetic, which then maps to the spectrum of this excursion algebra. And I'm saying this map is, you can easily see that this is non-constant. And it sends 1 to the sigma Arthur. And so that gives the contradiction. Is it OK? So it's just the simple thing about the structure of the Weil group, which is that if you have a local system, like because there's this Z quotient of the Weil group, like anytime you have something which centralizes your given local system, you can use that to just vary the local system by just changing the value of Frobenius using that element. And so this was also, I guess this was one of Arthur's really key ideas, was that somehow there are many annoyances in the Langlands program beyond GLN. So for GLN, if you have a cuspidal automorphic form, there's supposed to be this corresponding Langlands parameter, and that corresponding Langlands parameter should be irreducible in the cuspidal case. And one of the like original sins of groups beyond GLN is that their Langlands parameters don't have to be irreducible. Like you can have a cusp form, and the corresponding Langlands parameter might not be irreducible. And one of Arthur's ideas was that, first of all, you shouldn't really think about the class of cuspidal functions. It's not really the right notion. The right notion is sort of these discrete functions, these discrete automorphic forms. And the second thing is that the notion of Langlands parameter isn't quite a right notion. The correct notion is involves this SL2 also. And then the statement is once you fix these two things, then everything kind of works. So you'll end up with a, for these discrete parameters, you'll end up with a Langlands parameter of SL2 times the Weil group, which is irreducible. And so that's what I'm explaining here. Corollary is, in particular, for every cusp form, there exists an irreducible Arthur parameter. But even for cusp forms for general reductive groups, it may be non-trivial along this SL2 factor. And then I want to make a remark also, which is that Laurent and Laforgue proved that every irreducible like Lee's sheaf on X is iota pure. Let me just call it pure of some weight. I put iota, people who know, of some weight. And this is in Delitz's sense. And so the so this implies a similar statement for general. This just implies by Tanakian formalism, or however you want to say it, a similar statement for every group actually. And so this implies that our sigma arth is pure, really kind of weight 0 under this under these hypotheses. And so this implies Arthur's form of the Ramanujan conjecture for people who know. So the so the usual Ramanujan conjecture says that, in a suitable sense, the Hecke eigenvalues of a cuspidal automorphic form should look something like traces of unitary matrices, suitably generalized to arbitrary reductive groups. It was known to be false for SP4 since maybe work of Saito and Kurokawa. And Arthur suggested that sort of by incorporating this SL2, then you could correct this failure of the Ramanujan conjecture. And so that's what we're explaining here. Yeah, okay, that's...
So in this statement, you're using the interpretation of the Arthur parameter as a homomorphism from the Weil group to HL, or...
HE?
HE, yeah, sorry.
Yeah, or... Yeah, I mean, you can say it that way, or you can also just say, yeah. There's always these two ways to think. So you can, I mean, okay, I said it implies a similar statement for Weil group mapping to H, or you could also say it implies a similar statement for the Weil group times SL2 mapping to a connected reductive group.
And I'm supposed to know what weights mean in that context?
Yeah.
Okay.
For example, being pure of weight 0 essentially means that, or being, sorry, what am I trying to say? Okay, being pure of weight 0 means that whenever you take a representation of your group H, then you get something pure of weight 0. Being pure of some weight, so here the weights are indexed by, like, let's say I choose my iota.
No,
yeah.
sorry.
So,
I haven't said it from the perspective of the map to H. Never mind.
oh yeah, but then if it was the Veg group times SL2, it means if you just restrict along the Veg group factor, you get something pure of weight 0.
Oh.
That's all. You forget the SL2.
I see.
Yeah.
But then you start with a representation of G?
Yeah.
Uh-huh.
Yep.
Okay.
But the really key point is that when you do, like in practice, when you do that restriction, you're not getting the Langlands parameter if you just restrict stupidly along the first factor. To get the actual Langlands parameter, you have to incorporate the square root of q thing from the SL2. So that's sort of like, so in some sense, the thing of naively restricting to the Veg group would satisfy the naive Ramanujan conjecture, but that's not the Langlands parameter. The Langlands parameter involves this other correction. So, yeah. Other questions?
I just want to make sure I understand the cuspidal forms are those with eigenvalues are isolated point. If that's the definition.
No, for me the cuspidal forms are, okay, there's this constant term operation from sheaves, but also there's constant term operation for functions. And cuspidal forms are the ones whose constant terms vanish for every proper parabolic. That's what a cuspidal form is, or function. You know. There's a different characterization of them, which is that you can just take the space of compactly supported functions and take the vectors that are, like, let me just assume the group is semi-simple. Take the vectors that, when you act on them by the Hecke algebra, and take the span of all possible things that you obtain in that way, so if that's finite dimensional, then you're cuspidal, if and only if. So in other words, the cuspidal functions are the span of the honest Hecke eigenfunctions. So, but honest Hecke eigenfunctions, I include the compact support condition.
Sorry, can you repeat again the argument that why you can get this other parameters isolated ones?
Why it's an isolated point? Yes. So I'm saying that that's something very general. Just if you have any commutative ring, let's say, yeah. So you have to like wrap your head around the setup a little bit, which is the duality makes it slightly hard. So so let's think about what's actually happening here. Do I have space? So the situation was I have basically this ger E here. And I was saying that that's more or less up to this kind of fiddling about pluses and minuses, and in fact that's even irrelevant. That's just the same as the excursion algebra here. And so now when you take the span of your function f, too many e's, because f was an eigenfunction, well, this is some submodule under the excursion algebra. And so what that corresponds to in the excursion algebra is just a one-dimensional submodule of the excursion algebra. I'm saying this is just some commutative ring, and it's confusing. We don't usually have one-dimensional submodules of commutative rings. They have lots of one-dimensional quotients, not lots of one-dimensional submodules. And if you ask yourself, how can one-dimensional submodules occur, there's an interesting way, which is as associated maximal ideals inside of the ring. And that's what this example is saying. And there's a boring way, which is that your ring can just be a product of these two factors. And then you take this, and that'll be a submodule. And geometrically, what that's corresponding to is saying, like, OK, you can have some kind of like little, like here the geometric picture is like there's some little infinitesimal thing sticking up in this affine line. But I'm saying that if you're actually reduced, then your affine scheme will be a disjoint union of two pieces, one of which is whatever it is, and the other of which is just a point. So, yeah.
And so just to complement, if at the very beginning O was omega on the stack of parameters, that would imply that it's only isolated points by exactly this.
That is not correct.
But you would have the same duality. I mean, no, it's not correct.
Well,
because you could argue in the same, I mean, that any eigen, I mean, each time you have an eigenfunction, it would arise as a sub. I mean, if O is omega.
Yes.
And you can't argue as you just did in that case.
Well, you can, but the point is that you can't just diagonalize the operators on compactly supported functions. Because so to say, like, if you try to diagonalize something that's like Eisenstein, then you got an actual Eisenstein series, which isn't compactly supported. Yeah. 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 Yeah, and I guess what I was explaining before is that you can check. This is also sort of one of the known phenomena in the business, is that you're supposed to be able to ignore the SL2 exactly in the case that you have a Whittaker model. And that follows from what I was explaining before, that this zeroth term in the filtration, the nilpotent being 0, is exactly the span of the Poincare function. So yeah, so what this is saying is, like, if you, yeah.
Could you explain what Eisenstein series look like in this case of SL2?
In what sense?
In any sense you care to take it.
I feel like I'll just write down the definition of what Eisenstein series are. So,
maybe I'll try to find a better sense for my question. You can move on in the meantime if you like.
but let me I'll just.
Or how about this? Oh no, you're just gonna no. Never mind.
I'll probably just say nothing, but it's quick enough. So what I call Eisenstein series here, sometimes maybe it's better to call pseudo Eisenstein series. But so there's this operator where you do sort of pull back and push forward. So it means that you start with a function on this space of, well, maybe it's all of fq. So if you start with a function on line bundles on your curve, but a function with finite support, so it lives only on it's 0 away from finitely many degrees, then you form a function here by saying, for my given vector bundle E, I look at all possible extensions like this, and then I sum over the values of my initial function from there. That's called pseudo Eisenstein series. That's always sort of a very easy operation, so it's like a finite sum, because for a fixed degree, there's only finitely many such extensions. There's a more serious thing you can do. So what that forbids is taking an honest character of this Bun-GM of fq, because those don't have finite support. Yeah. Right? Characters don't take the value 0, famously. And so that's what the sort of like true theory of Eisenstein series is about, is like, if you start with something that doesn't have compact support, then you're going to form an infinite sum when you do this. And there are ways to manage that were more or less invented by Langlands.
But let's, on the dual side, let's say you have an SL2 parameter that's maybe semi-simple but not irreducible. So how am I seeing? So I have global sections over this whole space, which includes such parameters. Global sections of omega over this whole space, which includes such parameters. How am I
It's kind of similar to this picture where there's going to be some kind of quotient of the space of compactly supported functions, which is like tensoring over the excursion algebra with your point, and that's and then it's sort of I guess that projection onto that space is going to be given by something like a dot product with the honest Eisenstein series.
Okay. So then, okay.
So it's again sort of giving you a way to make sense of some. It's like there's some object that doesn't quite exist, but it exists in the quotient.
I understand. Okay.
Yeah.
So it's like, yeah, okay. I understand. Thank you.
Yep. Where I've totally lost track of where I am. Okay, so.
So in particular, you're seeing those Hecke eigenvalues in some quotient of your space of automorphic forms.
Yeah, I mean, yep. Because you see it, like, when we talk about we're talking about like some character from here to see it's a quotient, it's not a sub, usually. Other questions?
It maybe misunderstood what you're saying, what you just said, but Eisenstein series themselves typically have trivial arithmetic too, so they should be seen as something inside the function. There was this filtration on compactly supported functions, which was essentially given by the arithmetic too. But the arithmetic too of Eisenstein series in those concat pedals is trivial. So shouldn't they sit inside the functions of compact support, even though they don't have compact support?
Shouldn't they sit inside of the tempered functions, the zero theorem?
Yes, they are tempered, but maybe what you said would be applied to this. Never mind, I'm confused.
Okay. I mean, like you get the constant function as like a residue of Eisenstein series. So Eisenstein series do produce these like non-tempered parts of the spectrum also. Yeah. Okay. So I guess what I want to I probably have time to explain one thing, and the two things I would ideally like to explain are kind of where these line bundles come from and the construction of the map between the associated graded and the sections of the line bundle. But the other thing I could explain is why global sections of Loxis arithmetic looks the way I say it does. I think I'll do the first thing. There's no major. If anyone has a major objection, speak up. So where LE comes from, and the construction of the map from this GER-E to sections of LE. And this is a slightly funny construction. So what I'll do is.
Sorry, Sam, could I just make sure I understand the definition of this GER-E? So let's imagine, so E, we have our poset, we have E, we have the things that are less than it.
Yeah.
And we take the homotopy colimit of all the things that are global.
So when I say that it's Okay. So so what happened was I wrote just less than or equal to e, and then I also wrote less than e. But really, okay, it's for every downwardly closed thing. Yeah. So the fact that this is a filtration is I think what you're...
That doesn't just mean that the maps are injective. That means something more.
It means something more.
It means that when you collate all of the things that are less than e, that collation lives in degree 0 and is a subobject of the...
Yeah, I would say just the fact that it was a filtration in the... let me just make sure to...
Like if this were e and we just had two things less than it, then we'd be saying that the map from the direct sum into this is an injection, right?
Correct.
Yeah. Okay. And if it were three like this in a diamond, then we'd be saying that the push out sits inside. Yeah.
That's correct.
Okay.
Yeah. So.
And you're also saying that the homotopy push out is the same as the push out, or are you?
I am.
Okay. Good.
Yeah.
Okay. So it's absolutely the strongest thing.
It is absolutely the strongest thing possible. Yeah, that all is correct. And what I'm what I'm I should say fumbling at the moment is is that. In fact, just that's part of my definition of a filtration indexed by a poset. Is like, for this, like if it were like a square, I'm saying that the term for this downwardly closed set is the push out of the things that you're saying. Yeah. Okay. So. Other questions? Okay, so what we'll do is we'll construct the following data. So first, a gerb on this loxis HE restricted. So we're going to do everything kind of at the geometric level. So GE is a gerb. In other words, it's the data of kind of it's a point to B2 GM, or if you like, it's a twisted version of quasi-coherent sheaves. And in fact, this GE is going to have the property that its square is trivial. So this is kind of categorification of this line bundle LE. And then I'll also have a functor from this indco of loxis gcheck. And the restricted doesn't matter anymore. What I'm saying now makes sense in any context. So let me just be a little bit ambivalent. I'm going to have a functor from here to the gerb twisted version of this indco. And if I take this indco nilp less than or equal to e, then the map from here to here is going to factor through the category quasi-co inside of here. And then, and in fact, it's going to factor, it's going to give rise to a functor from indco nilp less than or equal to e mod indco nilp less than e into this quasi-co gerb twisted version of this loxis HE. And then the last step of the program is you take the trace of Frobenius. Oh, and it'll give rise to a functor like this, and you'll prove that this preserves compact objects. And so therefore, it makes sense to take the trace of Frobenius, and that's exactly going to give me a map from this GER-E of global sections of loxis G-check arithmetic with coefficients in omega to global sections of this loxis HE arithmetic with coefficients in some line bundle, which is itself the sort of, sometimes the trace of this gerb, some slightly enhanced sense. And so in order to do this, I have to tell you some so some kind of general Lie theory around nilpotent elements. So remember I have this Jacobson-Morozov SL2. So this gives rise to a grading on the Lie algebra. I'm going to take, for example, G-check greater than or equal to I. I'll just use notation like this to be the direct sum of J greater than or equal to I of the jth graded piece. So this G-check greater than or equal to 1 is nilpotent, well, for every I greater than 0. And so this integrates to some group. I should say, maybe a good way to think about what this construction that I'm going to explain is doing is that it's extracting some kind of Whittaker coefficient in some sense, but on the spectral side and for general nilpotent elements. So that's the kind of thing I'm trying to articulate here. And yeah, so this integrates to this G-check greater than or equal to 1. And so here's what people say. So OK, I guess I have this SL2. I'm going to write E. Yeah.
I suppose you applied some standard construction from the jar of GE to line bundle LE.
That's right. Yeah. Let me explain explicitly what the line bundle is, maybe after giving the discussion. Or, I mean, like, No. Yeah, I can. I mean, I can explain it very abstractly. So, so what am I trying to say? So, if you take this thing restricted, so what our gerb gives us is a map like this, and this gerb you can see is actually Frobenius equivariant. So on Frobenius fixed points, this is going to give rise to a map to the fixed points here under the identity, which is B mu2 times B2 of mu2. That's like sort of, usually is it OK? It's like usually you get G mod G if you take the fixed points under the identity of on BG. And so this maps canonically to B mu2, and in particular to BGM. So that's the construction. OK, so what you sort of what people say is you try to consider the homomorphism. So I choose kappa to be the killing form, let's say in the simple case. So you can consider this homomorphism from g check greater than or equal to 1 to k. But this is sort of a bad idea unless the grading is only by even numbers, because this is in degree -2. And so you're sort of, there's something a little bit off about it. And so what you're supposed to do instead is the following game. So there's this character, first of all, pairing with f. And then you also have the actual space g check 1, which is sort of greater than or equal to 1 mod greater than or equal to 2. And this is a symplectic vector space with the pairing between two elements given by kappa of f against the bracket between C1 and C2. And a good picture to have in mind for the sort of, and the fact that this is symplectic, that's non-degenerate, follows from the representation theory of SL2. And sort of a good picture to have in mind here is that you have this g check greater than or equal to 2. This is mapping via the character I just defined, size of f, to this one-dimensional vector space. Here's this g check greater than or equal to 1. Here's this g check 1. And I guess maybe from now on I'm going to call this v, because that's just the notation I use. Here's the push out. And in fact, this is a Heisenberg extension of v by k. So this is a Heisenberg extension. And so this is sort of what replaces this Heisenberg extension, in some sense, is kind of what might replace the character in the case of the principal nilpotent element. So now, so what's the gerb? So I guess let me give some so over this loxis HE, I have a sort of symplectic bundle whose fiber at a given local system is going to be the cohomology of x with coefficients in this v sigma, and I shift by 1. And this has an obvious, it's an orthogonal bundle. This has an obvious, so this formula with the shift by 1, you're supposed to think of as kind of the derived version of h1 of x with coefficients in this v twisted by sigma. V is the same one as above. So this v has a symplectic inner product. So this is the symplectic local system on x. And then when I try to cup the two classes together, I get -1 times -1 is an even inner product on this bundle. Good so far? And so you can form the corresponding Clifford algebra. And that gives rise to a gerb, essentially modules over the Clifford algebra. So that's what the gerb is. so there's a nice interpretation of this gerb. Yeah, maybe let me call this orthogonal bundle E, H. There's a nice interpretation of this gerb due to Pregel. Well, probably building on earlier works of Kapustin. Well, I don't know exactly the history. I learned it from a paper of Pregel. And so what is it? So basically it's, you do the following game. So you take this space of local systems. It has this orthogonal bundle. So this is some quadratic bundle, if you like. In particular, there's a canonical map down to A1 from here. So this is the quadratic form. Then you take indco on the fiber over 0. Basically, because this is the fiber over 0 of something, there's some quotient you can form. I guess I'll say this in a moment. There's some quotient. It's called matrix factorizations of Q, which is just a name. It's some kind of notation. And if you pass to the GM equivariant category on both sides, then it turns out that this is this indco twisted by the gerb on this space. I mean, this is something which works for any y. And what's this MF of Q? This is the following thing. So, so if you take indco on 0 times 0 over A1, this acts on anything that has the form f in, I can't call it f, phi inverse of 0 for any function phi. And this has this quotient category. So this is k of beta module. Why am I saying, am I wrong to say quotient? What's going on? Yeah, quotient category. And this has this quotient, which is k of beta plus or minus 1 modules. And so MF is obtained by tensoring up.
There's some weird thing with twofold cohomological shifts here. Like that, if you're saying that is indco twisted by the gerb, but doesn't that depend on exactly what you mean by how you twist a category by a gerb? Because this thing is a two-periodic category.
But the GM invariance eats up the two-periodicity.
Oh.
Yeah.
Okay.
So, like for me, what a gerb is basically a category with an action of quasi-co that's sort of invertible. Yeah, even better is the actual definition is it's locally trivial. Yeah, and so yeah, here I defined a category with an action, and then it's a yes or no question: is it a gerb? And yeah, but so the GM invariance here is like saying if I take like these sorts of modules in the Z-graded world, that's a category which is a little non-canonically equivalent to fact, maybe. Or different reasonable people might make different choices about the isomorphism they chose there. Yeah. And then how does the construction go? So so what I'm going to do is take locus, and then I'll take HE, semi-direct product, this G check greater than or equal to 1. So this HE, remember, was the centralizer of the full SL2. And so it really acts on everything coming from the Jacobson-Morozov theory. Of course, I should quotient by some GM, and you need a little bit of care about that, but let me not do it right now. And then what do I want to say? So now this is going to map down to locus HE semi-direct product with this Heisenberg for V. And then further, it'll map down to this locus HE semi-direct V. And this is our quadratic bundle in this case. And then further, it'll map down to locus HE. And everywhere, it's mod GM, mod GM. Let me just make a remark. So, OK, so this had this quadratic form Q that went down to A1. And so what I'd like to say is that this maps to Q inverse of 0. Because then what I can do is I can take a coherent sheaf, pull it back, push it forward, and then by design, intco on this space mapped down to this my category twisted by the gerb. And in order to do that, there's just a very beautiful, I mean, it's a very nice exercise somehow with Heisenberg groups, which is that if you think sort of what's happening, OK, so here there's a V. So just sort of ignore the HE everywhere. So this is basically locus of V. This is basically locus of the Heisenberg group. And what I'm doing is I'm saying V maps to BGA. That's sort of what the Heisenberg group is doing for you. So this is a homomorphism of stacks. And that lets me map from local systems for V to local systems for BGA. This is itself the cohomology of X with a shift by 2. And in particular, it maps down to just actual H2 of X. And that's my copy of this A1. And so, and the statement is that this diagram commutes. So that quadratic, if you unwind what the quadratic form is on this bundle, you can interpret it as mapping to locus BGA and then going down to this H2, which makes sense because of kind of what I explained the inner product on this space was. It was wedging and then sort of working in with the H2 itself, lens in H2. And maybe a small comment is that in the situation in which Frobenius is around, the restricted setting with Frobenius, you shouldn't really think of this as an A1. You should think of it, well, if you want to make this all Frobenius equivariant, you should remember that Frobenius is acting on here by multiplication by Q. And that's ultimately where the Q's come from in the story I was saying before. So anyway, OK, that was just some outline of the construction. So OK, thanks, everyone.
Yeah.
Is there some connection of this story we're here with, like, they representation?
Yeah. 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 I think that's how. Yeah. Maybe I should have said that this construction of the functor is really joint with Benz-V and Venkatesh. And I think that they think about this all as some spectral relative Langlands. The construction of the functor is joint with them. So basically the construction I was just explaining. Oh, the functor from, I would say, from here to here. Yeah. And then the various properties maybe are, I don't know, some complicated.
So that should be the spectral analog of generalized Whittaker coefficients,
Correct. Yeah, this is the spectral analog of generalized Whittaker coefficients.
which of course contain the Taylor series of their representations, which also have to answer that's its question, probably.
Yeah.
Mm-hmm.
Yep. So it's, I don't know exactly in what sense to say it's like the spectral analog of the Fay representation, but that's kind of the spirit.
So I believe there's a in the geometric setting that there's an understanding of the Fay representation before passing to Frobenius fixed points. I mean, you know, the Fay representation has some meaning in geometric Langlands.
On the automorphic side.
Yeah, on the automorphic side.
Yeah.
So then maybe there's, then it becomes purely a question in geometric Langlands to relate the two, right?
I wouldn't, but I'm not saying that this is Langlands dual to anything.
Okay, I'm asking though.
Oh, that's not, yeah, I don't want to say that at all. Yeah, in general, I don't know at all. There's a sort of very interesting question, which is like, there's these like generalized Whittaker models for arbitrary nilpotent elements, and what do they correspond to under Langlands duality? No idea. And so, and for me, this is kind of the spectral flipping A and B or something side of that question.
Okay.
What you're asking now? Yeah. I don't know the interpretation of these in terms of geometric things, and maybe if I did, this whole story would be a lot simpler in some sense. But
Maybe I can say, at least if we do everything arithmetically, on the spectral side, there is a classification of hyperspherical varieties which contains the iota. On the automorphic side, it gives you these generalized Whittaker models. On the Galois side, it gives you the R2 Basel 2. And because you seem to geometrize the R2 Basel 2, then it should be related, I think.
yeah, I mean that's essentially what's happening in this story. It's just that I'm not talking about. Yeah, I don't know what the like. Yeah. Anyway. Yeah, so that's the story. All right.
Which paper of Tony Traeger is this?
The big one about matrix factorization. I forget what it was called. Do you know the name? His thesis. Yeah. There's one that probably has the word matrix factorizations in it and in the title. And if you search Clifford algebras and Tolle Pregel, I think it's the only one that comes up on Google. It's the one that comes up first on Google. Yeah, but his thesis. Yeah. But you know, it's a nice exercise to try to prove also. Yeah, this interpretation of these.
And I have no idea how it would relate Clifford algebra to.
I can try it. I can tell you after the. I can tell you after the talk. Yeah.
And also this GER-E can be related to some filtration just on automorphic side.
Yeah.
Like we can do filtration on the singular support. Like for example in SL2 case that GER-E principle should have like trivial singular support. And
right.
How this GER-E is related to another filtration.
Okay, so the most direct construction I know of this filtration goes through derived geometric Satake. So you can extract the filtration from staring at derived Satake, essentially, and it'll give you the right filtration on the automorphic side. There's another filtration, which is the filtration by singular support. And that's a filtration by nilpotent elements in G, whereas this is a filtration by nilpotent elements in G check.
So we expect some like order reversing.
You might expect some order reversing thing, but yeah, there's this, I forget, it's called maybe Lustig-Spaltenstein duality, other names get attached to it. There's a map, a duality map, which is not it's an isomorphism for GLN, and it's not an isomorphism in general between nilpotent elements in G and G check. So it's a duality on what are called special nilpotent elements. And so there's a nice paper by Sergei Lysenko, which is contemplating exactly these kinds of questions in general. So it is known that sort of at the lowest and highest levels, like the zero in principle behave the way you're suggesting. That's known due to, I guess, my work with Joachim and then also a solo paper of Joachim's. And yeah, that's basically my full knowledge of the question.
At least in the classical theory, there is a conjecture that the maximal orbit in the wavefront set of any automorphic representation should be special. Do you have a geometric analog of this?
That's what Sergey is suggesting in his paper. Yeah. So it could be that like if you deal with the singular support of an automorphic sheaf, that you can ask for sort of like what's the largest nilpotent where the singular support is non-zero. And it could be that's always a special nilpotent. Definitely, I don't know any counterexample to that fact. But that's the kind of thing that Sergey is suggesting in his paper. So instead of wavefront set, you say singular support. But I have no way of testing that question. All right. Well, thanks.
Give Sam a hearty round of applause. His many wonderful lectures.